Hello viewers, welcome you all to the session on linear data structures. Linked lists are, as you all know, our fundamental data structure in computer science. They are crucial for various applications due to their dynamic nature. There are a few differences lie between arrays and linked lists. Unlike arrays, which store elements in contiguous memory locations, linked lists store elements in separate nodes. This means that elements in a linked list are not stored next to each other in memory. A linked list consists of interconnected nodes, and each node holds two parts, a data part and a reference part, the one which contains a pointer to the next node in the sequence. The first node is known as the head, and it points to the second node and so on. The last node, called the tail, points to null, indicating the end of the list. The greatest advantage of linked list is its dynamism in size. Linked lists can grow and shrink dynamically, which makes them more flexible than arrays, which have a fixed size. These linked lists allow us to perform efficient insertion and deletion operation on it. Inserting or deleting elements in a linked list can be more efficient because it involves just changing the pointers. So this is particularly advantageous when dealing with large data sets where frequent insertions and deletions are required. Now if we have to talk about the applications of linked lists, these linked lists are widely used in various applications. Such as implementing other data structures like stacks and queues, and in building complex structures such as hash tables and graphs. These are very helpful in scenarios where the size of the data set can change frequently. Let's talk about the anatomy of the linked list. A linked list is composed of individual nodes. Each node contains two components, data and a pointer, which is actually reference to the next node in the same sequence. This linked list starts with the first node called the head. The head node is the entry point to the list. The last node in the list has its pointer set to null, indicating the end of the list. So what is head? The first node in the linked list is termed as head. What does it contain? It contains data and a pointer to the next node. So this is very essential for accessing the entire list. It is through the head we access the entire list. So each node in the sequence holds data and reference to the next node. These nodes are linked sequentially, forming a chain. The last node in the linked list is called as the tail. Its pointer is set to null, signifying the end of the list. There are few types of linked lists, and they are categorized based on the structure and the direction of connections between these nodes. They are singly linked lists, doubly linked lists, and circular lists. In the case of a singly linked list, each node points to the next node. It allows traversal in only one direction, that is from head to tail. In the case of a doubly linked list, each node contains two pointers, one to the next node and one to the previous node. It allows traversal in both directions, making it more flexible and easier to navigate. The last node points back to the head and create a circular structure in the case of a circular linked list. These are all useful for applications that requires continuous loop traversal. As told earlier, one of the major advantage of linked list is its dynamic size. It can grow and shrink as needed. So it makes efficient insertion deletion operations. so it is easy to add or remove nodes without reallocation. It is suitable for scenarios that require dynamic data handling and frequent changes or modifications. So here are a few advantages of linked lists. As specified earlier, dynamic size is a major advantage of linked list. These are dynamic data structure, meaning that their size can be easily adjusted by adding or removing nodes as required. So this flexibility overcomes the limitations of fixed size arrays where the size must be determined upfront. We need to plan the size of the arrays before we start coding. But that disadvantage has been overcome in linked list. Another benefit of our linked list is the dynamic sizing, which leads to memory efficiency. It uses memory more efficiently than arrays because they do not require a predefined amount of memory. Memory is allocated as and how the nodes are added, which means we use only as much memory as needed. And adding or removing elements in the linked list does not require shifting of elements as how we do in arrays, but then we can just insert or delete a node by just simply updating the pointers, making these operations very efficient. So linked lists can grow and shrink dynamically, making them suitable for applications where the number of elements is unpredictable or frequently changing. So these are specifically used in creating other data structures like dynamic tables, stacks, and queues. This is also used in places where data highly fluctuates. So it also works on efficient usage of memory handling as against arrays. There are a few disadvantages of linked lists. One significant drawback is, again, their sequential access nature. Linked list can be accessed only sequentially, starting from the head of the list. This means that to find a specific element, we must have to traverse the list from the head node through each subsequent nodes until we reach the desired element. So this highly impacts the performance. In terms of time complexity, sequential access impacts the time complexity of various operations. For example, searching for an element in a linked list has a time complexity of big O of n, where n is the number of elements in the list. This is slower as compared to arrays where direct access to any element has a time complexity of big O of 1. 1 means it takes only the constant time for all the elements. Operations that require frequent access to elements such as searching can be less efficient in linked list as compared to arrays. So this inefficiency is particularly noticeable in the case of larger lists. In an array, we can directly access any elements by its index, making retrieval operation very fast. Linked list lacks in this capability, requiring us to start from the head and traverse the list sequentially. So arrays allow for random access to elements, providing quick and easy retrieval. But linked list does not support random access, which can be a serious limitation in certain applications. Applications that require frequent and fast access to elements may suffer in performance when using linked lists. And for large data sets, the time required to traverse the list can become a bottleneck. So these are all the operations of a linked list. Possible operations are insertion, deletion, and searching. And these insertion can be done in multiple places like at the beginning, in the middle, or at the end. In the case of inserting nodes in the beginning, all that we need to do is to create a new node and point the new node's next reference to the current head of the list and update the head to point to the new node. This operation is efficient with a time complexity of big O of 1. In the case of adding a node at the end of the list, we need to create a new node, traverse the list to find the last node, point the last node's next reference to the new node, and update the new node's next reference to null. So this operation has a time complexity of big O of n due to traversal. N is the number of elements. In the case of inserting node in the middle, we need to create a new node, traverse the list to find the node after which the new node will be inserted, update the new node's next reference to point to the successor node, and update the predecessor's node's next reference to point to the new node. This operation also has a time complexity of big O of n. In the case of deletion, nodes can be deleted from the beginning. So we need to update the head to point to the next node, and the old head node is automatically being removed. This operation is efficient with a time complexity of big O of 1. To delete a node towards the end of the list, traverse the list to find the second last node, update the second last node's next reference to null. This operation has a time complexity of big O of n. And in the case of deleting in the middle, traverse the list to find the node preceding the one to be deleted, update the preceding node's next reference to skip the deleted node, and point to the next node in the sequence. This operation has a time complexity of big O of n. In the case of searching process, we need to start from the head node, traverse the list node by node, compare each node's data with the target's value. If a match is found, return the node. If no match is found by the end of the list, return null or indicate the element is not present. The time complexity in searching the linked list is big O of n because in the worst case, you may need to travel the entire list. So few applications of linked lists. Linked lists are used to implement stacks as we specified in the earlier part of this video, where elements are added and removed from the top, and it follows a LIFO mechanism. It uses push operation where a new node is added at the beginning of the linked list. It also uses a pop operation where it removes the node from the beginning of the linked list. Both these operations have a time complexity of big O of 1. In the case of queues, linked lists are used to implement queues where elements are added at the end and removed from the beginning, which follows a FIFO mechanism. During the enqueuing operation, a new node is added at the end of the linked list. In the case of a dequeuing operation, it removes a node from the beginning of the linked list. So enqueue and dequeue operations are efficient with a time complexity of big O of 1. In the case of hash tables, it handles collisions through chaining. Each bucket of the hash table is a linked list. So when a collision occurs, the new element is added to the linked list at the corresponding bucket. So this approach ensures that hash table performance remains efficient even when collision occurs. In the case of graphs and trees, they are represented in terms of adjacency list representations. It is used to represent graph which uses adjacency lists. Each vertex in the graph has a linked list of edges representing adjacent vertices. So this representation is space efficient for sparse graphs and allows easy traversal of neighbors. In the case of binary trees and other trees, it can be used to implement where each node points to its children nodes. And in the case of memory management, Linked lists are used in dynamic memory management to keep track of free memory blocks. A linked list of free memory block is maintained, and when a block is freed, it is added back to the free list. So this efficient management of memory allocation and deallocation without fragment issues is an advantage of linked list. It is also used in garbage collection algorithms to manage and reclaim memory. Circular linked lists. It is a variation of the linked list structure where the last node of the list points to the first node or the head instead of pointing to null. So this creates a circular structure rather than a linear one. So each node in a circular linked list contains two parts, data and a pointer to the next node in sequence. I hope this video is of very great use to you. Thank you very much.